My name is Nathan Sturdivant, and I'm going to talk about analyzing and improving the use of the FastMap embedding in pathfinding tasks. This is work by my master's student, Reza Meshiaki, and also in collaboration with Dor Atzman. And what we're going to look at today are embeddings. And so a little bit of introduction on embeddings. On the right-hand side here, I have a map. This is a grid map where every state in that map has an X and Y location. And so that's an embedding because an X and Y location, we can actually use the locations of states to compute a heuristic between those states that is a bound on the true distance between those states. But in many problems, especially coming from grid maps, either maybe we don't have an embedding at all, or the embedding we have doesn't actually give us good heuristic values. And so we might want to build a new embedding. And so building a new embedding looks like this, where we can rearrange the states in the state space, we can assign new coordinates, and in that new coordinate system, we're going to get more accurate heuristic values. So there's a number of approaches that have been used for this. Differential heuristics are a method that was proposed back in 2009, and those are building an embedding in a L infinity space using an L infinity distance. In 2011, there was a paper that showed how to build optimal embeddings in Euclidean space, but this is a little bit expensive, so this isn't necessarily feasible for very large maps. Another approach that had been used in databases for building embeddings was called FastMap, or is called FastMap. And in 2018, there was an HCI paper that showed how this could be adapted to create heuristics for use in search problems. And so that's the approach we're going to be looking at today, is this 2018 paper on building heuristics. The paper here that I'm going to talk about is going to show how to combine FastMap and differential heuristics, or the idea of a differential embedding. And there's some additional insights in the paper about building pivots and some additive theory. I don't have time to go to all those details, but I'll point out where those are. The full details are in the paper. And then we have a deep study of FastMap performance, and we'll show that we've looked in quite a few additional maps and metrics over the original paper. And finally, we'll present a subset today. I'll present a subset of what's in the paper of single agent optimal search problems results, and also in the multi-agent meeting problem, which is a problem where a bunch of agents have to find somewhere to meet in the map. Okay, now one of the things we did is we proposed a unifying framework that allows us to see some of the similarities between things like differential heuristics and FastMap, and also to see some of the things that we could choose. What are the things we might change about a particular algorithm? And so I'm going to describe them here in sort of a parallel way, the differential heuristic and the FastMap embeddings. And that's going to allow us to understand better the similarities between the approaches. So differential heuristic, we're going to use this map, the same map we'll use a couple different times in the talk, and we're going to build an embedding from it with the differential heuristic. And the way that this works is that we select a pivot, and I'll talk about how we do that in a little bit. And then what we do is we're going to embed in one dimension. We'll do this repeatedly for as many dimensions as we want to have. We're going to embed every state relative to that pivot. So the pivot is going to be at location 0, and for any other state in the world, it's going to be embedded at that state will be embedded at a location, which is the distance from that pivot. And so here, the red state is the pivot, and then we're embedding based on the distance from that pivot in the graph. And then if we want to do this again, we can. We can choose a new pivot, and we can do a second embedding here. Now, if I want a heuristic between two states, I can look up their x and y coordinate in this entire new embedding here. And now what I do is I take the maximum of either the x difference or the y difference to give me a heuristic. And so that's the L infinity norm. For pivot selection, there's a lot of different ways this can be done of different computational cost. The easiest way to do this is to choose a random state, let your first pivot be the state that's farthest from that one, and then successively, your next pivots are simply the state that is farthest from all existing pivots. You can do a better job than this. One of the best ways to do this that approximates optimality is using subset selection, but this can be quite expensive in practice. We did a lot of experiments to evaluate this and found that not only is it quite slow, you have to do a lot of work to get large improvements. So we're going to use this very simple furthest selection technique in the talk today and in the paper. FastMap heuristics are doing something similar. So we're going to select, instead of a single pivot, we're going to use two pivots. And again, I'll talk about how those pivots are selected in a moment. And then we're going to embed the graph using a slightly different embedding function here. It's based on the distance from a state to the pivot in both directions, and also the distance between the pivots from each other. And so what this is essentially doing is interpolating a state. How far is it between the two pivots? That's going to tell me where I'm going to place it. So here I've chosen two pivots, which are the red states, and then we're placing them across the world. And our first embedding, puts one pivot on one side and the other pivot on the other side. We can repeat this again, and we're going to actually repeat it again on exactly the same graph. And we can do this because we're doing residual distances, and I'll talk about that on the next slide. But we can now choose two more pivots and allows us to pull this graph out. What's really interesting here is because we're using residual distances in the graph, we're able to actually add the results together. So the heuristic is not L infinity, the max in each dimension, but it's actually the sum of each dimension. And that can be really powerful. Additive heuristics have been well studied. There's a theory of what you need to get additive heuristics. FastMaps actually conform to that theory. And so that adding together is a great idea. So what are the residuals? So imagine I have an input graph here where E and B are going to be my pivots. When I do the embedding, I'd get something like this. In fact, I would get exactly this, where we're only looking at the horizontal distances here. The vertical is just so that I can see all the states. And what I do is I'm going to get a residual graph at the end. The residual graph here is basically saying, look, and we do this for every edge. Between C and B, there's an edge cost 1. In here, between C and B, the actual cost is 1/2. And so what that means is that I can take the 1 minus the 1/2 that's been captured, and in the residual, I have 1/2 of that distance is left waiting to be embedded. And so when I look at my residual graph here, there's some nice distances. I can use those distances to build a second embedding, and they're going to allow me to capture more and more of the residual in the graph. And because I'm using that residual, I can add together the results. In terms of selecting pivots, in FastMap, the first pivot is going to be selected very similarly to what we did in a differential heuristic. We choose a random state, we get the farthest state from that, and then we get the farthest state from that first pivot to get the second pivot. And then that path between those states is what we're using as sort of going to be the main dimension of our embedding. And we can repeat that repeatedly and not get the same pivots because the residual distances are going to change, and therefore the pivots that we get are going to change. But there's a problem with this approach, which is if I want to build two independent FastMap embeddings and take the maximum from them, there's nothing here that takes into account any heuristic that I have already. And so we would actually tend to get the same embedding over and over and over again, but we describe how to fix this. I'll say a little bit about that in a minute. Okay. If I want to combine FastMap and differential heuristic, then this is one of the main contributions of the paper. The question is, can we do this? And the answer here is, at some level we can, but something funny is going to happen that didn't happen with FastMap. So we have our input graph like we had before. The differential embedding here, remember everything is the distance from E. So D, C, B, F, and G are all 2 steps away from E. So they all get embedded at location 2 in this embedding. And then if I were to compute the residual, what we see is the majority of edges are actually, in the residual, will have a cost of 0. And it's not hard to show, but I can't describe it well in the time I have for this talk, that basically the distance in the residual graph, if you use a differential heuristic embedding function between any 2 states, will always be 0. Basically, the path from any 2 states going back through the pivot will always be 0. And so what that says is, well, we could use a differential heuristic, but if you can use it, you can only use it once, because after that, there'll be no residual left to capture. Now, that may seem like, well, that's disappointing, we can only use it once, but it ends up that actually a differential heuristic is capturing a lot of residual, and we get to add it together because it's still part of the FastMap process, and because we can add it together, this is going to be very powerful. So we're going to demonstrate here. On the left-hand side, we'll show FastMap. This is a 2-dimensional FastMap. And the right-hand side, we have FastMap where the second dimension is a differential heuristic. If we watch the embedding that we build here, it looks identical for both sides for the first dimension. But when we go to the second dimension, on the left side, we see using FastMap. On the right side, we see a differential heuristic. Now, it may not be totally obvious, from looking at this that the one on the right is much better, but we can see many more states, many more dark areas. And what's happening here is we can distinguish many more states. And therefore, when we measure distances between them, we can capture much larger heuristic values in practice. Now, I mentioned before that the FastMap isn't taking into account the existing heuristic. And so we also proposed a new pivot selection scheme that basically, when you're choosing a pivot, you not only look at the distance in the graph, but you also look at the distance in the existing heuristic that we have. When we combine those together, then we can choose pivots in a way that avoids that we get the same pivots over and over again. And we'll see that impact in the experimental results. So we started by actually doing a really deep study of FastMap to validate that we had a good implementation and to make sure we understood the performance. In the FastMap paper, the majority of the results actually reporting two things. They're either reporting the median or they're reporting the number of problems in which FastMap outperformed other approaches. And so if we look here at the median performance at the 50% line, this is a set of problems on the map that's shown up there. We've sorted the difficulty from the easiest to the hardest for each of these algorithms. At the median performance there, the 50% line, we see that FastMap does outperform the differential heuristic. And we actually see on a majority of problems, FastMap does outperform the differential heuristic. However, on the last 25% of problems, FastMap does significantly more work than differential heuristic does. And this is because there's a long tail of very, very hard problems that FastMap doesn't do well on. We can also see here on this distribution that FastMap with a differential heuristic actually does much better on this particular map. And so that's just a hint at the performance we're going to see in a moment. So if we look at a subset of the results, again, there's much more in the actual paper here. These are the results that basically were in the original paper. FastMap here is doing slightly worse because we're using benchmark problems, and the benchmark problems have a long tail of very hard problems in them. The differential heuristic is doing about the same here in the median, but if we look at the mean, it's much worse. And actually across all of these, in Dragon Age, it's a little less than a factor of 2, but it's about a factor of 3 in these other maps here. So this is actually really bad, and it's worse than we expected it to be. But we do see that if we take FastMap and we add a differential heuristic to it, that in practice, we are actually able to do, we always improve the performance of FastMap by using the differential heuristic at the end. Additionally, we see in Dragon Age maps that we did beat the performance of differential heuristics, where in StarCraft and Room maps, we don't. There's some other maps, sometimes we do better, sometimes we don't, depending on the map set in the paper. When we look at a 24-dimensional embedding, then we can see a few other things here I want to highlight. So one, we see in room maps, it's really interesting actually. The best performance in room maps is built by building 8 3-dimensional embeddings, 3-dimensional FastMap using a differential heuristic for the last dimension of the embedding. We have the same mean performance, but much better median. The means are they're within the 95% confidence interval. When we look at mazes, actually, the best thing to do is to build a 24-dimensional embedding. If we do 24 dimensions of FastMap, it's actually worse than differential heuristic. But when we use differential heuristic as the 24th dimension, then we're actually doing better. And the other thing we see here in Dragon Age, this is very consistent with the original paper, is that actually combining together FastMap and differential heuristics sometimes actually gives you good performance too. If we look at the multi-agent meeting problem, we see things, this confirms things are consistent here. The median and the mean always correspond, so we're only showing the mean here. But we see that on Dragon Age, we're doing much better. On StarCraft, we're doing slightly better by adding the differential heuristic, but still better and statistically significant. And then on city maps, we're actually doing much worse. So to conclude here, so I'm going to just show the embeddings here of maze maps. You can see the difference between these two. But this paper has done a very deep study of FastMap and showed how the differential heuristics can be combined and are able to get much better heuristic results or performance and heuristic search problems as a result. And so if you're going to be using FastMap for doing an embedding, you really should be using the differential heuristic for your last embedding. It's a it's like a one-line change in the code, but it gives this nice jump in performance. So thank you for listening to this talk, and if you have more questions, you're always welcome to contact me or to find me at the conference. Thanks.